Well, let's get started. Welcome back, everyone. We're now in week 13 in the 16-week semester, so we're definitely getting through the content. The big announcement we have to start us out today is our third exam information is now all posted. And just this morning, I've sent out the information along with the link to schedule your exam. If you have any trouble finding that information, don't hesitate to ask about it. I'll be happy to send another link or a new email. You can find that in the Canvas messaging system and also in your ISU email address. But pretty much it's going to just be the same rigmarole that we did for both exams 1 and exams 2. Only difference is we have different content. And I started by writing out this content on Friday that was going to include Unit 8A, but I felt like the exam was getting a little bit too long, a little too disjointed. It made more sense to me after making a revision to just keep it in Chapter 5 on statistical reasoning. So these are going to be the 5 units on our third exam. As before, there's a formula sheet, but this one's less of actual formula sheet and more just a list of common definitions. That way, when you go to write your page of notes, just like on the other exams, this will inform you on what you don't have to duplicate, so that'll save you some time. Also, there's 2 versions of the sample exam. Version 1 is just our ordinary lecture notes converted into worksheets. And version 2 is brand new problems that we'll take a look into as well. Well, any questions whatsoever, folks, about the upcoming third exam? Thanks for asking about that, Amy. Yes, I did put into the information when I was writing down the exam information in the testing centers, a ruler is allowed, so you're welcome to bring one. That might be helpful because I'll be asking you to construct at least one graph, similar to what we were doing in Unit 5C, I believe that was. Yep, absolutely. Thanks for asking about that. Other questions at the moment? Okay, again, as far as the exam preparation goes, probably one of the first things you'd want to do is start compiling your page of notes. It'll be one page, both sides allowed, handwritten or printed out, it's up to you. And beyond that, get caught up on the quizzes relative to these units, be caught up on MyLab, and you'll have a really good idea of what's on the real exam. On Thursday of this week, just like the other exams, we're going to hold a in-class review for the entire class. And so I'll be happy to take questions. If there's not a whole lot of questions, that's all right as well. I'll probably select randomly assorted questions on a unit by unit basis from version 2. But come armed with questions, a student-directed review is usually superior to randomly selecting questions on any one of these sample exams. And they can be questions from anything, random questions out of the textbook, quiz problems you're welcome to discuss as well. Quizzes are, what, like we mentioned, primarily a participation credit. They could be questions that we've seen before in the lecture notes, MyLab questions, anything would be fair game. But aside from that, what we'll be doing for Monday and Wednesday's class is moving forward in the schedule. We'll be working through these 2 units, probably finishing Unit 8B today, and then working through 8C on Wednesday's class. Well, that's our goal so far. This is going to be a week going into third exam, so we'll be reviewing quite a lot on Thursday's class. But any last questions or comments at all, folks, before we get started? Okay, well, let's jump in. We'll talk more about the exam on Wednesday and definitely on Thursday during the review. Currently, we're in Unit 8B, Doubling Time and Half-Life. And Chapter 8 is kind of nice in a way because it's a humongous change of pace. This was mainly analyzing context, working through technical definitions and statistics, analyzing graphs. Here, we're now calculating stuff like we've been doing before. And by the way, this section we're in is very calculator heavy, but we're also going to look into new things, computing logarithms. So it'll be a good idea to have your calculator nearby for today's class, really any class as well, just for the sake of practice. But we're going to be doing some new things on today's class using the log button for some of the computations. So I'll be demonstrating the use of both this calculator and the TI-30XA as those problems come up. First, it hasn't been too heavy with what we've been dealing with the calculator. For these problems, it's been basically take a number, multiply by either 2 or a half, raised to an exponent. And for the refresher on what we left on Thursday's class, we're looking into the approximate half-life formula. This is the fourth formula already on these notes, so we're going to do a formula recap, a roundup of formulas. But it was telling us if something is decaying exponentially, instead of exponential growth, something is shrinking in this way, then we have a notion of a half-life, the time it's going to take for half of the amount, whatever quantity it could be, to vanish. We take the decay rate, drop the percent symbol, and just take 70 divided by p. So this is the rule of 70 for exponential decay. And our formula gives us a way to find the fractional amount something's decayed by. That's the 1/2 raised to the power of t to the power of 1/2. Excuse me, 1/2 raised to the power of t divided by 1/2 is the way to say that. Some problems focus on this part right here. Other problems focus on obtaining the new value like we see on part B. So just another part of the recap. Let's recall that this part is called the fractional. Amount. The quantity decays by. Sometimes we're going to compute just the part in green, and other times in the problem is almost randomly, we use both values like we did in the part B. So this problem was telling us that the total acreage of looks like a rainforest in the island of Borneo is declining approximately 2% per year. So to find the half-life, we just took 70, dropped the percentage, and we found a 2% per year decline means half of the forest is going to be gone every 35 years. So then we were asked if there's currently 400 square kilometers of the forest on that particular island, how much is going to remain in 40 years? More than one half-life goes by. We took the initial value of 400,000, multiply by a half to the power of the amount of time t divided by the half-life. And this is what we got in our calculator, 181,144.7 kilometers squared. So we'll be practicing more formulas just like this. And our major part of the notes that we're going to look into is how do we go beyond an approximate half-life formula with a heavy limitation breaks down for decay rates over 15% into something more exact. But any questions whatsoever, folks, with the recap? Okay, well, because it's been a long weekend, well, I guess they're all kind of short, but it's been a weekend, and there's 4 formulas we've already looked into in this page of notes. Let's do a quick formula roundup just to warm up before we go into the new content. So we're looking into 2 kinds of growths, exponential growth, exponential decay. I guess that's not 2 types of growths. We're looking into exponential growth and another kind of exponential change, exponential decay. So let's call this first column in our table type of change. And then for the next 2 entries, we'll look into exponential growth. and exponential decay. So we have that type of change to consider first. Aside from that, we also have a time that's incredibly important. It's either a half-life time or a doubling time. The formulas are all approximate. We put those little squiggly lines there to say we're approximating. So we'll call this next column header approximate time. So if we're talking about exponential growth, the time we're referring to really is the doubling time. How long does it take for quantity t to double in its value? So I think we usually used green for that part for t half or t double. So let's keep that color coding going. T double is going to be 70 divided by p, where p has to be interpreted as the growth rate or the decay rate that we'll see if it's exponential decay. So that's one thing we have to find in each one of these problems. What is p? If we're talking about exponential decay, here's where the formulas become kind of interesting in a certain sense. It's exactly the same formula. Really, it's just the context that's telling you if something's increasing or decreasing. And the other part of the formula is going to show us how it increases or how it decreases. So really, even though there is 4 formulas so far, this is the same exact thing on the right-hand side. If it's exponential decay, we call it t half for half-life. And it's 70 divided by p, just like we did in the part A of this question. So that's our formula roundup so far. For the next column, what we're going to put in is the full formula for using both the green part as well as the initial value. So we can call this the new value in time t. So that's a decent way to indicate it. Any questions at the moment, folks, with the build up at the table? Okay, so here's our next set of formulas. Again, let's call it new value. In time t. When we say time t here, we're thinking much like in the last question. They're asking what is the new value, amount of area remaining in a time of 40 years. So that was the specific t value in that question. If it's exponential growth, the formula is going to look like this. New value equals initial value we multiply that against, let me fix my color coding there, multiply that against 2 raised to the power of t divided by t double. So once we have the approximate doubling time, let me put a little approximation symbol there just to emphasize those are approximations. Once we have that approximate time, doubling time, this is our formula. And if it's exponential decay, the formula changes a little bit. It becomes new value equals initial value times. Here's where I recall making a couple mistakes on the lecture notes on Thursday. Must have been tired. If it's exponential decay, it's not 2. It's going to be 1/2 raised to the power of t divided by t half. So that's our format. And the major observation in this formula is whether you're using 2 or 1/2, it's all about if something is growing in the problem or something is shrinking, decaying exponentially or growing exponentially. So even though there's 4 formulas here, if you look at it really closely, it's really like one formula with one key difference. The context will tell you if something's growing exponentially, so we use base 2, or if it's decaying, we'll use base 1/2. So that's our roundup into one spot, all of our formulas. We're going to practice exponential decay just a little bit more. and then turn to the topic of, if you want to be more precise and not say approximate every single time, we'll give those formulas as well. Okay, I think we're ready to get into the next question. Any last thoughts or questions, folks, about this table so far? Okay, well, putting this table to use, here's the last question before we switch gears and look into exact doubling time, exact half-life. So this is the Thwaites Glacier, often called the Doomsday Glacier. This is a real glacier out there in the world. It has an ice shelf that's rapidly disintegrating, and we're told global temperature shifts, warming ocean currents are causing the stable surface area of the Thwaites ice shelf in Antarctica to decline at a rate of 7% per year. So that's a pretty big decline rate. First thing we want to discover about this problem is if we take this data as fully accurate for every year, well, something's shrinking here. So we're being asked, what is the half-life of this problem? So here's our handy set of formulas down below for reference. In order to get the half-life, we have to determine what is the P in this problem. So we begin, let's say here we have P equals 7 coming from this portion right here. P is just the percent change, whether it's in a growth or a decay situation. It's declining at a rate of 7% per year. And because it's declining, we can say that T half, following these formulas here, specifically that cell, but they're identical, except for what name we give it. T half is going to be 70. Divide by 7. Our strategy here is whatever the percent change is, we peel off the percent sign. That's the P in the formula. Then just divide, but that's a fast division. This will give us 10 altogether. If it was per year, the unit analysis would give us just 10 years exactly altogether. So the half-life for the Thwaites Glacier, so-called Doomsday Glacier, is 10 years. Any questions at all, folks, with getting that approximate half-life? I should put an approximate symbol right here, but any questions so far? Okay, next part of the question is asking what fraction of the ice shelf's surface area will remain in 30 years? And that's always a pretty awkward question. We mentioned a little bit that the notes that we're writing here are pretty similar to the problems in the textbook and my lab. When it's talking about fractional decay or fractional growth, it's always referring to, I think I'm looking at the wrong spot. Sorry, I thought I had my spot here. Let me just go to where we started. Yeah, we wrote a comment down just for a quick reference. Sorry for the random scrolling. When it's asking for the fractional amount and a quantity decays by, it's just referring to this whole part right here. So the next question we're looking into didn't give us an initial value of how much area that glacier covers currently. We're just wondering, for the given half-life, what is this quantity going to turn into if we're looking into a time scale of 30 years altogether? So the fractional surface area change is referring to just the part of the formula, specifically in green. And it's also weird because it's fractional in the sense that we take 1/2 raised to a power of t, divide by t half. The fractional part is the 1/2 here, but we still put the whole thing into a calculator and get a value out after we're done. So we're still going to round this to one decimal place, write it as a decimal, even though they're asking a fractional amount. I think the reason that they use this in the exercise is just to give us kind of a key word that we're using just that part of the formula. So we already have the half-life, the so-called T half that's written there. All we need is the time frame. That comes directly out of the question. It's asking for 30 years. So this whole computation is going to turn into 1/2, divide by 30 years, divide by 10 years. Because years cancels off, we usually just write it more clean like this, 30 divided by 10. But once we do the computation here, it becomes a little bit more straightforward. We get 1/2 raised to the power 3 altogether on this. But that's because if the half-life is every 10 years, and 30 years have gone by, this 3 is just saying it's been 3 half-lives. So you take a half times a half times a half is effectively all this is saying. Take 1/2, raise that to the power of 3 altogether, and we get 0.125. This says round to one decimal place. You know, that's kind of blunt on this one. I think the rounding could have been a little bit better. Let's make a small change on this. I think for the specific values, let's round to 3 decimal places. Makes a little bit more sense. Sorry for the random update here on the rounding. A little bit more sense on the context. So we'll go with a 0.125. So that's it, folks. That's the fractional decay rate for this particular ice shelf. Any questions or comments whatsoever getting through this one? Okay, well, so far we're pretty much through the main questions that you're going to see in the homework notes. The next thing we're going to address is, what do we have to do if we want the exact formula for both doubling time and half-life, which is appropriate because there's a warning for both of these formulas that it breaks down if the growth rate or the decay rate exceeds 15%. So it's a valuable formula to have just in case we're in one of those more extreme situations. Here's where we're going to practice the calculator quite a bit more just to get some practice with dealing with logarithms because the formulas are stated in terms of those logarithms. So here is that next portion of the notes. Here we're going to briefly define what we mean by logarithm in the very first place, do a few computations, just getting comfortable with how this works in the calculator before we go on to the next set of formulas. And in a real sense, this is kind of a warm-up as well. We're not going to use logarithms in the Unit 8C, but in Unit 8D, that seems to be pretty much what the whole thing is all about, applications with logarithms specifically. So think of this as kind of our introduction, and then they're going to come back quite a bit later after exam 3. Well, first, here's its definition. A logarithm, or just log, is an exponent. And in a way that's comforting. You know, the course started out with us practicing a lot with exponential notation, whether we're dealing with, say, powers of 10, 10 power 5 divided by 10 power 17, and even weirder kinds of powers of 10. So we're just looking into expanding on our work on exponents that we did at the very start of the semester, way back in chapter 2. In this book, the author mentions we're only going to look into base 10 logarithms, also called common logs. And here's how the specific base 10 logarithm is defined. The base 10 logarithm of x is the exponent that 10 must be raised to in order to yield x. It's kind of a word salad, so the reason there's so much white space here is really just to understand that one sentence right here to see what it's saying exactly, and also practice with the calculators. So the computation, or the button that we're going to be using, is this right here. So that's our log button. if we're using the TI-30 X2S and you wrote down something like this. Log base 10 is the exponent that 10 must be raised to in order to yield X. Let's suppose we put 1,000 in there. So we have the exponent, 10 must be raised to, in order to yield X. In this problem, the X is 1,000. The 1,000 is kind of a nice number in a certain sense. It's just a power of the base 10 itself. And if we use scientific notation, we could just rewrite that as log base 10 of 10 to the power 3 itself. So I didn't do much here. All I did is reformat the 1,000 into 10 power 3. But now if you check out in a calculator, I'll use Desmos to demonstrate it since this one isn't going to output anything. In Desmos, if I type log, it's automatically assuming I mean log base 10, or I'm using that button effectively. So give it log 1,000, and the output is just 3 itself. So let's think about that all together. The value of log base 10 is an exponent. So that's what it was telling us right altogether. It means it's the exponent. In other words, it's equal directly to an exponent. Our exponent is 3. And 3 must be the exponent or the power that 10 itself must be raised to in order to yield our X value, 1,000. If we do a really fast check, 10 to the power 3 is absolutely 1,000 altogether. Doesn't hurt to throw it into this calculator as well for emphasis. 10 power 3 definitely comes out as 1,000, tying together that concept. So effectively, whatever the output is right here, when we type it into the calculator, if you put it on the 10 to make it an exponent, it will result in the thing you started with, the input to the logarithm itself, that 1,000. So that's working with logarithms at the moment. If you practice in your calculator, the way it should look when you go to type it in is about like this. Let me get a new pen. It's going to show up. Hit the log key here in pink. It'll show a log. Use the parentheses to throw in 10, close the parentheses, and then the output to that will give you a 3 altogether after you hit the enter button. So I guess the other keys that you definitely need are going to be the parentheses keys as well. Well, if you practice that in your calculator, you should be getting a 3 if you're using this model. If you're using the TI-30XA, we'll show how that goes as well. But any questions at the moment, folks, with the logarithms?
I do. You said that you put log and then in parentheses 10. Wouldn't it be parentheses 1,000? Why 10?
Oh, sorry, yeah. Absolutely 1,000. I forgot what I was throwing in there. I was throwing in the base on accident. Thanks for mentioning that. That should have been absolutely, as you said. Let me see if I can control Z that right there. Hang on, it's not letting me take it off. That should have been 1,000 right here. Yeah, if we throw in, say, 10 inside the logarithm, that's going to come out as just a 1. Thanks for spotting that weird typo there, weird error there. Other questions at the moment? Okay, so throw this into the calculator, log 1,000, close the parentheses, actually put in the input 1,000 there, and you'll get the exponent 3. Now let's turn over to the other calculator. I think this calculator is convenient, but you might have learned how to do plenty of operations in a totally different calculator. So then this one's no longer convenient. So in the TI-30XA, everything goes a little bit different. We're using very similar keys. We have to use the log key here, and depending on what we're doing, we sometimes have to use the parentheses keys as well, just not for this particular problem. But I'll highlight them nonetheless, just to emphasize they're going to be needed for some of the other problems that we're going to see on the notes. In the TI-30XA, the way to get log base 1000 is first key in 1000 after you have 1000 on the screen, then hit the log button. Let me put that to the test. So if you're using this calculator today, hit 1000, then you don't have to worry about the parentheses on this one. Immediately hit the log button and your screen will show a 3 right at that spot. So we work inside, let's focus on this part, work inside the input first, then work outside, just hitting the log button. Then if you work in those steps, you'll get a 3 as well. Either case you do it, you should get that log of 1000 comes out as exactly 3. So there's our second calculator. Any questions at all, folks, using this one here?
So for this one specifically for the log button, it's always going to be log base 10? Or is there a different number that you can have after for the base?
You know, some textbooks, some math books could be lots of different kinds of bases. If you're looking at this one, ln, it's another logarithm, but the base is the number e, which is approximately 2.71 and some change. Here it is, the number e. There's that weird number. And it might be, in some context, appropriate to do log base 2, log base 3, 5, and so on. But in our specific class, in this particular book, we're only ever going to be using log base 10. So that's the only button that we'd ever need for the logarithms in this class. Other questions about that so far? Okay, maybe just one more random computation, just for the sake of practice. If we went and computed log base 10 of, you know, things like 1000, things like 10, or even 100, these are all very convenient values. These are values that we really didn't even need a calculator really to come up with the exponent. For example, if we do log base 10 to the power 7, it's just 7, and it's in no way a coincidence whatsoever that we're getting the exponent when we put 10 up, put on the power of 10 whatsoever. So if we do something more random and not put in 10 to a power, maybe you threw in 13, just some random number, that's okay too. The calculator doesn't care. It's going to find the approximate exponent that you have to take and raise 10 to in order to result in 13, which it's not an easy exponent to come up with, but the calculator does this in a pretty rapid way. In the TI-30XA, all you would have to hit is 13, so your screen shows a 13 right here. Then hit the log button, the one highlighted in pink over here. And this is what I would get to, let's take maybe 5 decimal places. Log base 10 of 13 is 1.11394. So that's kind of random. It's saying if you raise 10 to the power of 1.11394, keep in mind it was an approximation, so this isn't perfect, but 10 to that exponent should be really, really close to 13. So in other words, 10 to the power of 1.11394 is just about 13. And we can get as close to 13 as we would like by taking more and more digits on this number here to get closer and closer to the 13. Checking that out in the calculator, here's what it would look like. Take 10 to the power 1.11 And you know what? Already at the nearest hundredth, that's close. This would round to 13 if you're rounding to the nearest one. But it's also 394 were the actual digits we took. And that's really, really close at altogether 6 significant digits. This rounds, if we're rounding to the nearest, say, thousandth place, to 13 very easily. So the calculator is a pretty powerful tool to come up with these exponents. Any number you put here, convenient or weird, we're going to focus more on the weird ones for the problems we're going to solve below. All it's giving you is the exponent that you raise 10 to in order to get the thing you threw inside, 13 in this case. Well, that's our really quick rundown for exponents so far. All we're really doing in this formula is going to use exponents for a couple formulas. But then once again, in Unit 8D, we'll be returning to logarithms, discussing more applications related to them specifically. Well, any last questions or thoughts, folks, on just the cranking out these values side or the interpretations? Okay, well, let's return to the main topic of these notes. We're looking into exponential growth, exponential decay, and our goal is to improve the approximate doubling time, the approximate half-life time. So that's what these next two formulas are going to be all about. And they are really quite tricky. Let's actually carry down this table one more side so we can see them and compare methods all at once against the new set of formulas. So those are the old formulas above, the approximate doubling time or half-life time. And now we're going to look into the exact doubling time, exact half-life later on and below in these notes, starting with this one, doubling time. And here's the one major comment to make right away. When you're using this so-called rule of 70 in either one of these cases, the major comment that we always made was P, we just drop the percent sign. We don't actually convert it to a decimal number. And that's, again, very weird. This is probably the only formula where that's ever going to happen. So both here and here, do not convert to a decimal. We just drop the percent symbol. Which makes our new formula kind of gives us a bit of whiplash in a certain sense. Because when we use this formula, the fractional growth rate or the fractional decay rate, R, it comes in as a percentage. So this value R given here is used in just one spot in the formula. And in example 9, we're looking into the Boise metropolitan area, which has a growth rate of 2.5%. That's the R value in this one. Or let me not put it down like that. Let me come back to that. The major idea is with this formula, we go back to the typical way we would work with any percentage. R now must be converted to a decimal. So if we're stated a value of 2.5%, that is the growth rate R in this problem, but R as a decimal must be R equals, converting back to a decimal just means divided by 100, which just means shoot the decimal place 2 spots to the left. So it's going to be 0.025 in this problem. So as a decimal, we'd be using that. And we only do that if we're using the exact doubling time formula. If we're using the approximate doubling time or half-life formulas, then we do the jarring thing of not converting to a decimal whatsoever. So again, we've kind of harped on this weird step right here because it becomes pretty jarring coming back to the exact formulas when we go back to our old ways of converting things into a decimal as usual, like we might have done for compound interest and so on. Well, any questions, folks, at all with the new formula or the new procedure with dealing with the growth rate? Okay, well, as far as the formula itself, other than the massive issue on dealing with R and converting it, here it is. If something is growing exponentially, and you know the percentage growth rate, or as our author likes to call it, the fractional growth rate, if you happen to know that value, throw it into log base 10 of 2, that's the numerator each and every time, divide by log base 10 of 1 plus the growth rate as a decimal, and that's the exact doubling time in the problem. So we'll practice working with this new formula. In the example below, we'll look at the exact half-life formula, practice it as well. So here's the example 9 context. Again, it's really brief. It just says, historically, the Boise metropolitan area has seen periods of rapid expansion with a steady growth rate of 2.5% and a current population of around 850,000 people. That current population is probably going to be our initial value in a problem. So let's pull that together by highlighting it. But first, here's what part A is asking us to do. It says compare the doubling times found with the approximate and the exact doubling time formulas for the Boise's metropolitan area, rounded to 4 decimal places. So the idea with what example 9 part A is all about is how far off if we're using the approximate doubling time versus to what we're about to start using, the exact doubling time. We're going to see how close they or how different they really come out as. Well, let's give this a try. Let's probably organize as well by first starting. Let's do the formula that's fast first. Let's go for the low-hanging fruit and say approximate doubling time. This one's really fast. All we have to do is take t double equals approximately 70 divided by, and it's weird because see the notes above, this growth rate of 2.5%, in the formula, no conversion, drop the percent sign, 2.5, then back in the calculator, just simply 70 divide 2.5 to give us 28 years altogether. No need to round on that first part. So if we use the approximate doubling time formula, we have that. But now we want to see how is it going to come out if we did this exactly. No approximation whatsoever. Well, any questions at all, folks, before we go to the exact doubling time? Okay, here's where we need to practice with the calculator a little bit more, kind of the purpose of the last page of the notes. The exact doubling time. We still call it t double like before. It's going to be equal to, here we're just going to use a dead-on exact equals and start throwing in the information. This is going to be log base 10 of 2. Divide by log base 10 of 1 plus. Then this R value was a 2.5%, but we're converting it over to a 0.025. And so that's the entire quantity that needs to go into the calculator. So let's practice working these out. I'll show it 3 different ways. If you have your calculator handy right now, give it a try. I'll show on Desmos. This will be our answer we're going to check against. And then we'll try it out on the TI-30XA as well as the TI-30X2S, just to see how it goes. So first, if you've already gotten an interior calculator, here's the value to check it against. Log base 10 of 2 would just look like that in Desmos over log base 10 of 1 plus 0.025. Or it's just as fine to say 1.25, but if you typed it in verbatim as you see it on paper, that's what it would look like. Then, hang on, that's the wrong decimal. I was wondering how I got to 3 years. That's a big change from 28 years. Definitely put in the 0.25. So if you add them together, it'd be 1.025. If you go with the 0.25 here, the correct value we converted it over to 4 decimal places, we get 28.0710. Years. So we got it, folks. The exact doubling time has quite a bit of extra accuracy. This was assuming an approximate doubling time of 28 years. And we see that we're off by just a little bit more than 7/100ths of a year. In a lot of contexts, that might not be a very big deal, especially if you're forecasting values. In other contexts, that could be a really big deal. These kind of formulas apply to situations where money's growing, for example, and you wouldn't want to ever be shortchanged any amount. Well, we did it, folks. That's the doing it through Desmos. Now let's practice on the TI-30XS, showing what it would look like. On this calculator here, the way I'd probably type it in is just one line in this screen, hit the log button, way over here where the red dot is, to type in log base 2. Then make sure you're opening the parentheses to put the 2 inside that logarithm. Hit the division symbol and then go log of 1 plus 0.025. In that calculator, if you put it all together in that particular way, you should be getting this value out. Anyone have any issues using that particular calculator, getting that value? Okay, next, the tricky calculator is always this one. So here's the operations I would take for this. And there's 2 good strategies here, 2 good schools of thought for doing this one. For these particular calculators, not a bad idea to just add these numbers together just to save a step, but it's not strictly required. And also one thing you can do just to break this up if you prefer is to go log 2, that'd be getting the numerator, then divide by log 1 plus 0.025, that'd be getting the denominator, just divide the 2 quantities, and that should give you this value. The trouble is it's tedious, and if the problem asks you to round to 4 decimal places, you're probably going to want to keep 6 or 7 decimal places here, so it's a lot of writing, a lot of typing. So here's another way to do this. I've learned how to do this based off our compound interest section. No, I think this was the loan payment section actually, where we were looking into this. This was a student suggestion on you can actually put this in one step, where, well, in one line without breaking it in 2 like this. So if you're trying to do this all at once and not break it into 2 parts, first thing you want to hit is 2 right here. Let me go in stages to make sure it's working out. Once that 2 is put in, you want to hit the log button so you have the logarithm of 2 for your numerator. So hit that button for log base 10. Now I've got essentially this part you see on Desmos, the numerator portion. But we have to divide it, so the next step you take is hit that division key right away. Once that division key is hit, if you had some nastier numbers right here and you want to put this in without adding or subtracting them, hit the parenthesis button. I'll hit parenthesis and then go 1 plus 0.025 After that, hit the close parenthesis. Hang on, I think I messed it up. Let me try it one more time. It's 2 log divide by, then parenthesis 1 plus, then 0.025, then close the parenthesis, and I should be looking at 1.025. That's what you should have at that step.
I just tried it out on mine, and you don't even have to do the parentheses part. If you do the numerator log 2 divide by, and then 1.025, and then log again, then you get the
Your
denominator.
way.
If you hit the equals symbol, then it will do the whole number out in one line.
Gotcha. Yeah, I was showing how you would do it if you wanted the parentheses in, but I would definitely agree with you. For this particular problem, way better to just add that in your head, right? To skip that extra problem there and then just go right to that answer. Let me try doing it out exactly the way you suggested. So start
Oh,
with,
sorry, didn't mean to interrupt you. I usually do the parentheses, but I just found out that I didn't have to. So I thought I'd mention it.
that is really helpful. I'm glad you did. Because yeah, for this problem right here, I think the parentheses is, I mean, I messed up on the first try as well on trying to get that to work. So probably not even worth it. So let's go 2 log division, then exactly as you said, 1.025, hit log, and now we've got to that number right at that step. Just hit enter one more time, and it remembers that we said division. And now we're at the 28.0710. So yeah, thank you for suggesting that. I think that's a much cleaner way in hindsight on putting this problem into that particular calculator. Other questions at the moment? Okay, and again, the more and more you practice with this calculator, it's really not that bad. The only reason I kind of like this one is I can type it in one go and I can see if I made a mistake because it's just right there staring at me. I'm gonna have to use a left arrow, right arrow to see the whole thing. But this calculator is the one that's used more often than not in a laboratory setting for a lot of different classes. So you might just have a lot of practice in that particular calculator, which would make sense to want to use this one in particular. It's the one you're really good at. So either way you do it, even if you break up numerator, denominator, get those values out, and then just divide the two, we're coming up with 28.0710 years. Any last questions or comments at all, folks, with the computation side of this one? Okay, well, now that we have that, here's the follow-up question. It says, use the exact doubling time formula. And when I write the problems, I'm going to try to always be really specific, whether it's going to be the approximate doubling time or the exact doubling time. In the problems, I'll try to bake that into the answer so we know which one we're using, because now we have 2 different approaches, which can be kind of hectic for the wording of the problems. So using the exact doubling time formula, this one, calculate the projected population in 20 years. So we're looking to amount T is 20 years altogether. But that means we're pretty much just using this table again. We're looking into the exponential growth row. So it's going to be this formula right here that we're about to use. Really, the only change that we made with this table below was we didn't use the approximate doubling time. We're using the exact doubling time that we came up with. So we're just slightly more accurate now that we go to calculate this value. So we want the projected population in 20 years. We can say the Boise metropolitan area. I'll just say metro for short. Area population. The equality is just a literal is. We take an initial value following this formula, but that's what this current population was here, 865,000 people. We multiply that against the fractional growth rate, that's 2 to the power of t divided by the doubling time, t double. So 2 to the power of, for the variable t that's here by the red dot, we're just using the 20 years they told us to use in the problem. So we're looking into the year 2046. Divide by the half-life. Almost one half-life has gone by, so we're expecting pretty close, but below double that amount. So divide by 28.0710. So this will give us altogether, back to a calculator again, this population size. So 865,000 times 2 to the power 20 divided by that decimal number there, 28.071 does the job, but let me throw in the 0 since we wrote it down. Let me try to also fix my penmanship there. That's a 0 at the end. And this is going to be the new figure. Let me take a close look at that. I've got 865. I was expecting a different value on there. Oh, I think I see my problem. What was throwing me off is the number 924,000, has barely changed from 865,000, right? They're pretty close, but 20 years has gone by, which is almost 2/3 of the way of an entire doubling time. I should have been dealing with a number way bigger than this. My mistake is in the denominator. I put 208 instead of 28. So let's fix that. Put in the actual 28.0710. That looks a little bit more appropriate. That's now in the millions, about 1.4 million. So let's put in the value 1417. (404) people in 20 years. So if everything just keeps on going the same way as it has been in Boise, growing at 2.5% per year, they're looking at a metropolitan area getting closer and closer to almost 1.5 million people. That's quite a lot for an Idaho town. But any questions at all, folks, getting through this one? Okay, well, once again, these formulas aren't so bad if we're just looking at this grouping right here. But once we loop in the exact doubling time formula, it muddies the water because what we have to do with the value P, what we have to do with the growth rate R is different. R needs to always be converted into a decimal. I think that's one of the reasons why the author used R. It reminds us that that's kind of like an interest rate, an APR. We're taking the same step. And he used a special symbol here, P, because now he's doing something really, really different. So along those same exact similar lines, here's our next set of formulas we're going to look into. Our goal is to find the exact half-life for exponential decay. Here's what the formula looks like. If you look at this really, really carefully, based on what we saw in the last section notes, the formula looks really, really close, but it is actually different. In this table, the formulas were identical, which was kind of a nice mathematical miracle in a certain sense. But here, that's one key difference right there where the red dot is. There's an absolute negative sign we have to be worried about. So when we're dealing with half-life, we're still using log base 10 of 2 divided by log base 10 of 1 plus r, but there's a negative sign right there. And it gets even worse, in my opinion. I wrote this down in the same way that it's shown in the textbook. I felt like it's fair to copy them down verbatim. If this formula comes up in the textbook, it looks exactly like this. But when our author emphasized this part and uses a plus here, it's easy to get a little bit confused and it's kind of vague what's being meant. When we go to use this formula, in fact, right where the red dot is, because our author admits R is negative, you actually put a negative sign there. That's really jarring as well. Why didn't the author put a negative sign like this in the formula? Because then it's double negation, and that would mean plus right here. So this formula is even more tricky than the last one in that sense. So we're going to take our time with this one. Let's put down just a couple key warnings for these notes as we see them here. Like before, these P's just drop. The percent sign is all you do if you're using the approximate half-life or doubling time. But here, if we're using the rate R, then R must be written as a decimal and has a negative sign. So R being negative gives the negative sign to this R value that's going to go right there. So really, in fact, in the calculator, when you use this formula, there are two negative signs, one at the very start of the problem, and then you're really doing 1 minus some percentage as a decimal number. So extra tricky kind of stuff. These are kind of problems that definitely don't want to rush through. That's why we're taking the extra time today to think about all these tiny little things to watch out for. Any questions whatsoever, folks, with the weird minutia, the small details with this formula? Okay, and here's another one of these problems where I need to remind myself to practice how to pronounce some of these words. This is in Finland, and these are real places. I'm just going to try my best. We're told the Onkalo Spent Nuclear Fuel Repository and Olkiluoto, Finland, is the world's first permanent deep geological repository for high-level nuclear waste, spent nuclear fuel and otherwise. And for these kinds of repositories, this is a real place. These are real places that people consider and plan building. This one has been built. A common regulatory assessment period for deep geological repositories, again, this is for nuclear waste, is 250,000 years. So these are very, very impressive engineering projects to try to build something that endures that amount of time. I think a lot of people would probably say it's nearly impossible, but we still try. It says next, suppose the repository seals away approximately 65 metric tons. A metric ton is 1,000 kilograms. Had a brain sleep right there. So 1 metric ton is 1,000 kilograms, and we have 65 metric tons. 1 metric ton weighing about the amount of a small compact car. 65 metric tons of plutonium-239 is being sealed away. So we're going to say our initial time is today, right now. The vault is closed. We've sealed away this spent nuclear fuel, plutonium-239. We know a little bit about this particular isotope of plutonium. Scientific measurements indicate that plutonium-239 has a fractional decay rate of 0.0028776% per year. Even though it's radioactive, it's actually really stable, which in some ways is kind of unfortunate. So there's our fractional decay rate. But when it says decay, that conveyed a negative sign. Also, it's given as a percentage, so we have to do two things at once on this decay rate R. We have to convert it into a decimal and negate it all at the same time. So here's what we're going to be using all together. R is negative 0. Converting this to a decimal means we're going to divide by 100, which just means this decimal point moves 2 places more to the left. So it inserts 2 extra zeros, and then it's the 002876. So basically nothing, but it will disintegrate over time. And our hope is that at the end of 250,000 years, whether there's humans around or not, all of this is gone because this is just deadly to life. Whether it's going to be used for nefarious purposes or otherwise, I mean, it's highly radioactive. So that's the setup of the problem so far. We want to use the exact half-life formula to compute the half-life of plutonium-239 and round it to the nearest integer. It's a tricky computation because of everything that's going on with it. But you know what's great about a tricky computation like this is you have a pretty good check available to you. The check is that, the approximation. Let's start with the check. So that way, if we make a mistake in the calculator, we'll know right away if we're way off when we try to plug in this value. So again, it's kind of an unusual problem. It didn't ask for the approximate amount. It wants just the dead on exact. We're still going to do this one as a check. The check would be that T half-life plutonium-239 is 70 divided by, but when we use this rule of thumb here, we're using that number. We're not putting a negative in front of it at all. We're using that number, just drop the percent sign. So it's 0.002876. Let's throw that into the calculator. 70 divided by 0.002876. And we're rounding to the nearest integer, so the nearest year. This to the nearest year is 24,339 years. Our value, when we use the exact formula, needs to be really, really close to that. And I feel like this is a problem I don't necessarily want to rush through. If you plugged it into the calculator already, then good on you. Let's show it in Desmos, but then when we come back on Wednesday, we'll practice both calculators again and do it more carefully. But in Desmos, this is going to be negative log for log base 10 of 2, divide by log, then it's 1, but you in fact have a negative sign here. Again, the formula is kind of annoying in a certain sense. The author has to write it this way to be mathematically correct, but it just makes it weird the way you use it. You really put a negative there because you're using that value, 0.00002876. And here's what this one comes out as. To the nearest year, it's 24,101 year, which is pretty close to this, telling us we're on the right track. But again, it's a tricky computation. If you've got to this value already, I'd say you're pretty well set for this entire unit as far as the calculator use goes. But we'll return to this, double check it some more, practice with it a little bit more on our Wednesday's class. But any last questions or comments at all, folks, before we call it a night? Okay, well, this will be the last unit, or excuse me, the last example of Unit 8A. Unit 8C, we're going to look into the so-called real population growth, but we're really just going to be doing a lot of the same similar things we've been doing in this unit right here. Well, have a great night, folks. I'll see you all in Wednesday's class. We'll finish this off before moving into the next unit. Take care.